Hello, in keeping with the theme of math is everywhere, today I want to look at quality control and Six Sigma certification. Six Sigma is a distinction granted to companies or organizations whose processes yield very few defects or errors. Six Sigma accreditation is particularly important for manufacturing and process engineering, but it can be sought by virtually any organization, whether public or private, nonprofit, or profitable. Limiting the number of defects ensures customers get a high-quality product or service that matches their expectation. Defects can be qualified by various measures. For example, a part could have the wrong dimensions, a metal alloy could have the wrong composition, a prescription drug could fail to meet a minimum purity guideline. Service industries can also receive Six Sigma certification. Defects in service industries could result in customer complaints. They could be as simple as too many burnt pieces of toast at a diner, or too much variance in portion or presentation at a restaurant. They could be false convictions in a court of law, or cases of police brutality. They could take the form of grammar or spelling errors in a series of documents, or of computer program bugs, errors in lines of code. They could be erroneous medical diagnoses at a hospital, false positives or false negatives in a disease test. They could be accounting errors, many other examples. Achieving Six Sigma process management is no simple task, as it requires an organization to actively develop strategies to decrease rates of defect or error and sustain those extraordinarily low levels. So I've got some math stuff here on the Excel spreadsheet. Let's look at, first, this is a mean, right? Mean or average, right? X bar or mu, and that's the sum of all of our data points over the number of data points. So if we had like a list of 1,000 numbers, we would add all those numbers together, divide by 1,000 to get the mean. Then our standard deviation, S or sigma, in this case little s because we're looking at a sample standard deviation. If we have car parts coming off of a factory assembly line and we want to ensure that they meet certain minimum quality guidelines, then we'll take a sample of those. We're not going to measure and inspect every last little product. We'll take some sample of those, and so the formula to find the standard deviation for that sample is just the number that we collect minus 1, just to account for the difference between the sample and the whole population. Big N is the whole population, but we're going to just take that minus 1. So to find the standard deviation, we're going to take the individual data points, that's xi here. So we've got 1,000 data points, and we're going to subtract from that the mean, right? That's, remember, all the data added up divided by the number of data points. And so say we have 1,000, right? So we're going to take each of those 1,000 data points, subtract it from the mean, subtract from that the mean, we're going to square it, that'll give a positive number, and then we're going to add all of those things together, divide by 1,000 minus 1, or 999. That'll give us our standard deviation. And we're going to see that about 68%, if our data is normally distributed, then we're going to see about 68% of our data falls within one standard deviation, one of these things, to the left or to the right of the mean. Right? So if we're looking at a part size, it's going to be within one standard deviation bigger than the mean, or one standard deviation smaller than the mean. And then if we carry that out to the second standard deviation, we'll find that about 95% of our data points, that would be about 950 in our 1,000, fall within 2 standard deviations, and then at about 3 standard deviations we're dealing with over 99%, 99.6 some percent, and 3.4 standard deviations we're dealing with pretty much everything, right? So that would be normally distributed data. Now, if we want to have almost perfect operations, we want to have, we're producing millions and millions of products, we're serving hundreds of thousands of customers, or we're making thousands of meals per year, whatever the service or product is, then we want a very low rate of error so that, again, we can develop that sustainable competitive advantage compared to other businesses, so that when customers come to our place, or in the case of non-market services like education, or government organizations like courts of law and police departments, we want low error rates, in order to better serve the population, right? And so over the long term, we want to have almost no errors. And so that's where Six Sigma, that's what Six Sigma means, right? And so Six Sigma does this thing called, they're shifting the standard deviation plus and minus 1 1.5. They're shifting the mean plus and minus 1.5 standard deviations, right? And that ensures that over the long run, given a worst case scenario, say that one day or 1 week or 1 month or in some batch, the mean is somehow very far away from where it's supposed to be. And in order to get all of the data over the long run within the range of tolerance, right, which is a very low error rate, then we want 6 sigmas, 6 standard deviations to the right and to the left before we can qualify as 6 sigma. And so it's a little bit broader, right? So outliers in a regular set of normally distributed data would be out in this range, right? But in 6 sigma, we're going to carry that out and be even more precise. Basically, we're looking to be more effective. We're looking to be more precise and have fewer errors, right? So that's why we do that sigma shift there. You can look it up online. There's plenty of websites. I did a quick Google search and found various websites that I'll reference a couple here in a moment. We can get into that in a different video, maybe. Okay, so imagine, here's our test case. Here's our example. Imagine we're some engineers, we're making a product. Maybe it's some kind of a dowel or some kind of a pin or a rod or a cylinder or a washer of some kind. And our ideal diameter is 15 millimeters. And we have a tolerance range. Our customer needs 15 millimeters plus or minus 0.0015 millimeters. Right? Anything greater than 15.0015 millimeters, anything less than 14.9985 millimeters is a defect. We can't use it. And so we're developing this product. We start a test run, right? And we put our machines together. We create X number of products. We take a sample, right? And here's our sample. I've highlighted using conditional formatting, right? Greater than and less than our tolerance levels here. I've used conditional formatting to show which of these products are defects. So we took a sample of 99 and we got some defects. We got 4 that are greater than 15.0015. We got 3 that are less than 14.9985. Right? So the probability of defect, which is just the number of errors divided by the sample population, 7 divided by 99 is 0.07071. That's the probability of defect. Pretty simple. And so I multiply that by 1 million to come up with, this is an important measure in Six Sigma certification and studies here. DPMO, defects per million opportunities. Now this is predicted because, again, we don't have a sample of 1 million. Right? I took a sample of 99, I found 7 errors. I calculated the percent of error, which is the probability of defect, as we're estimating here. And then we can multiply that by 1 million. 7% of 1 million is 70,708, rounded up because we can't have 0.07 defective products, so I rounded up to nearest 1. Right, so here's our DPMO. Right? And so we're going to take that number, go over to a table. Right? Some of you have seen z-score tables. Right? Theirs is very, very similar. So we're looking at a table, and we are at 70,000. So we're with a 1.5 sigma shift because we want to make sure that our products are stable over the long run. So we're at between these two numbers here, 66,810 and 80,762. And so to get an approximation, we go through a little bit of quick math. Subtract we can make the difference here, divide that by the number of predicted defects, and we get along our normal curve, we're looking for about 0.19, about 20% the way between the two values on the table, right? So we're about 20% the way between 2.9 and 3.0, right? So we're going to take 0.1, we're going to multiply that by, oops, it should be 0.19732, and add that to 2.9. And again, this is an approximation because a normal curve is just that. It's a curve, and so we can't, this is just a linear approximation, but it does give us a rough estimate pretty close to our sigma value here, our process sigma. And so it says we got a process sigma of 2.9. Well, we've also got technology here, and so we had 99 cases, 7 defects, and 2.97. Again, rough estimate, 2.9. That's our process sigma. We are not close to achieving Six Sigma processes, so we're not getting certified. So we go back, we test our sensors, we recalibrate, right, and then we do another trial. Right? In this trial, I took 195 in the sample. Right? We still have the same tolerance range, we still have the same defect range, right? And so again, I've used conditional formatting greater than 15.0015, less than 14.9915 to highlight those data points, those cylinders that we made, which are outside of our tolerance range. Our customer will not take it, right? So our mean, you know, we're tightly grouped around the mean, basically. We have a pretty well structured distribution here, but we do have some outliers, or we do have some defects. They're not outliers because we are approximately normally distributed, right? We do have some outliers. We've got 5 greater and 3 less than our tolerance, right? So 8 divided by 195 is 0.041. That's our probability of defect, right? And then we're going to take and multiply that by a million to get our PDMO. 41,025 plus 1, 41,026. Go back to that table. 41,026. So we are between 3.3 and 3.2. Where exactly between 3.3 and 3.2? Well, we can get a slightly better indication by taking, again, a linear estimation on the normal curve by just looking at what percent of the way between those two numbers we are and multiplying that and calculating out that number right there, 3.22 or 3.2. We're closer to 3.2 than to 3.3, and so to get a better estimate, we can go back to the calculator, which is a little more accurate, and it says 3.24, again, and a good rough approximation of our process sigma. Still not even close to Six Sigma quality, right? We have way too many errors. So we recalibrate our machines. Maybe we get a little budgetary, little bit of a windfall, and we can buy some new sensors. Maybe we can test out some different shifts with different machine operators. We adjust things, and we go back and test again. This time, just to ensure that we aren't suffering from a small sample size, we take a slightly larger sample, and we're still finding a couple errors. They're highlighted using conditional formatting, greater than and less than our defect levels. We've got 3. We got 1 greater than our maximum diameter. We got 1 less than our maximum diameter. So our probability of defect is shrinking. So what we're doing in the factory is working. Right? We're getting more tightly grouped around the mean here. And our number of predicted defects per million opportunities, opportunity means sample, or per million output, whatever, it's getting smaller. So we're at 10,169. We're going to go back to our Six Sigma table. 10,169 is between 3.8 and 3.9. We're still not even close. Right? We can do a little bit of rough calculation to see if we're at 3.8 or 3.9. Right? We're not even anywhere near where we need to be. We can go back to, let's see, 295 and 3. We can go back to our Six Sigma calculator and get a slightly better estimation of our process sigma, 3.82. So this is pretty difficult. So we hire some consultants, and they come in and they tell us that we're using the machines incorrectly, and we recalibrate using their technology, and maybe we make some other changes. And we take a larger sample size just to make sure that, again, we're not suffering from low sample, because it's getting really important. This is our 4th trial, right? And okay, we've got over 1,000 and we've only got 1 defect this time. That's pretty good, 1 in 1,000, right? So that puts us squarely within that 3 sigma range, which we've been at for a while. Right? If we go back here, we're well within this normal curve. We don't have outliers, but are we 6 sigma? Right? Are we that hallmark global standard of quality? I mean, that data looks okay. It's very tightly grouped around the mean. Let's look. We got 1 that's greater than our tolerance. So we made 14,000 products. Sorry, 1,400 products, 1,400, and we got 1 defect. Is our customer going to be happy? Well, I don't know. That depends. The probability of defect, 0.00071. That's pretty low. 712 per million. So imagine if Apple were making an iPhone, or imagine if Samsung were making a phone, and they had 1 defect per 1,403 phones. I don't think the customer who got that phone would be very happy. That's not 6 sigma, right? So to get to 6 sigma, you have to basically eliminate all of your company's errors. 4.69, right? And so let's say we took 10,000 and got 1. We're still not at 6 sigma. If we had a sample of 10,000, we only had 1 defect. Let's say we had 100,000, we got 1 defect. We're still not at 6 sigma. Again, companies deal with products and services in the hundreds of thousands, in the millions, right? Over time, this is the long run. That's why we do that 1.5 shift. That's why we broaden the range here, right? If it were just in the short term, just today, well, we've done a pretty good job. Even in this first one, we did a decent job. In the second one, we did a much better job. In the third one, we're really getting there. And by the fourth one, well, for today, that's pretty good. But if we're dealing with hundreds of thousands and even millions, let's add a 0. We're looking for 3.4 defects. Really, 3 defects. But statistically, say we can have 0.4 statistically. So 3 defects per million. Let's do a quick search. How many phones did Apple sell in 2019? They sold 40.8 million phones. And let's just guess that Apple's 6 sigma, but we'll ask anyway. Is Apple a 6 sigma company? There we go. Jobs integrated. Let's see. Never settling for anything less than the best. Apple is above all a company for which 6 sigma, lean, and Kaizen are all important. Okay. So 40.8 million phones. If they were 6 sigma, 40.8 million phones. Oh, let's go back to our calculator here. $800,000. How many defects do we have? Well, it's going to be roughly 3 times 40. Well, there you go. 100. All right, so they've got, if they're sold 40 million, if they're 6 sigma, then they've got roughly 100, 120, 100. I doubt they even have 150. Nope, not even 150 errors or defective phones that just don't work from day one among those 40 million. And all of their suppliers, all of their tier 1, tier 2, tier 3 suppliers, just like auto companies, deal to each other more than they deal to the general public. So in order for a major manufacturer to achieve 6 sigma, that means all of their supply chain likewise have to has to deliver a product that has very, very low defect rate so that the transistors don't blow, or in the clothing, the stitches don't blow out, right? So to sum up, Six Sigma ensures a level of quality. Could be in processes, could be in services, could be in manufacturing on an assembly line. In order to get there, companies have to take pretty radical action to reduce the level of defects in their products or services. Right, so I hope this gave a brief glimpse into what Six Sigma is and how it relates to central limit theorem and standard deviations and means and such. Thank you.